Welcome back to our Algebra 2 series, where today we're continuing our work in the rational roots theorem. Here's an example of a problem that could be factored, but it would take a little bit of time to evaluate how to work this out. That 21 and that 8x squared could be broken up so that we use part of it with a difference of squares with the 9, and then that would remain a 7 left over here. But I'm not going to get into that today. Instead, we're going to use this entirely by the synthetic division method. The nice part about it is 1, 3, and 9 are the only possibilities. And right away we notice that even though the coefficients here, 9, 21, 8, 3, and 1, do not add to 0, that gives us a positive remainder. But we do notice that if we added 9 and 8 and 3 and 1 as positive numbers, we would get 21, and then this 21 could be subtracted, and we would get 0. So in class, we notice that when that happens, what we want to do is we want to try -1 in our synthetic division to see what happens. Because once in a while, actually quite often, it works. So we're going to see if that happens here. 21 here and then a 9. And of course, our goal is to produce a 0 right here. Using the -1 then, um, let me just work down through here. This is going to be -4, it looks like. 4 and then 25. And here's a situation where it doesn't work. It's interesting to notice that we're going to end up with a negative remainder there, and so it does not work. And also take note that between 1 and -1, between 1 and -1, we have got a sign change. So something's going on in this problem to produce a sign change between 1 and -1. And because of that, I'm going to back this up and say, all right, we got to start over again. In this case, the -1 did not work, produced an answer that was negative, and so we're a little bit in trouble because we don't know where to go with this. The signs do not alternate, and they're not the same sign, so I can't rule out positives or negatives. So we'll just try a 3 and see what happens here. As we test this 3, we get 1. Here's a 3 here and then a 0, so that's interesting. Um, -8, -24. This looks like it's actually going to work now. And then -9. So once you anticipate, you're going to start seeing, hey, here it comes, pretty close. And then in the next part, we'd like to do this again. And once again, we notice that 9 will not be an option anymore because what's left over here is just a 3. So we know that we can only test 3's and -3's. So let's give it a try one more time with a 3 and see what happens. In this case, there's a 1. This will be a 3. That's going to be a 9. 1, 3, and by golly, it worked. So we ended up getting the 0 both times. Whoa, that's a very ugly happy face. Okay, it's a happy face with a mustache. Um, so in the end, we end up with an x minus 3 quantity squared. We did that twice, and we ended up with x squared plus 3x plus 1. B squared minus 4ac looks like it's going to produce some answers here for us. So this one we're going to need to use the quadratic formula to find the roots. X is going to be equal to 3. And in the case of no more rational roots, but in this case we have some irrational roots. X is going to be equal to -3 plus or minus, and then we end up with 9 minus 4. This is all over 2. So answers here 3, and that's a double root. -3 plus or minus radical 5 all over 2. There you go. Now, before we move on, I'm going to do one example where, in this case, all we're going to do is list out our possible rational roots. This is a beast because notice that the 49 right there makes it so that all of these terms are collectively um, relatively prime. And if we take the 24 in the numerator and the 30 in the denominator, and I like to factor these guys out, that's going to give me a 1, a 2, 3, 4, 6, 8, 12, and 24. And your denominator is going to be 1, 2, 3, 5, 6. Oh, golly. 10, 15, and 30. So this problem is one of those that I would consider virtually impossible to work out. We have, just to check them off here, 1, 2, 3, 4, 5, 6, 7, 8 possibilities of just integers, and then many more when I combine those as fractions. For example, when I take the 2 in the numerator with the 3 in the denominator, or the 5 in the denominator, or the 15 in the denominator, I'm going to create for myself 3 more fractional possibilities. And the same thing with the 4 and the 6. And I'll have many more opportunities to create new um, possible values. So if I'm going to get something to work from here, I'm going to try to do this by what I call isolation. I'm going to use the integers to try to isolate roots that are fractional. For example, if I test the number 2 and my remainder is positive, and I test the number 3 and my remainder is negative, then I'm going to look for a fraction that's right in between. Now, this problem would be fairly rigorous if all we wanted to do is just list out how many possible rational roots there are. This could take us quite some time. But for the purposes of this video, I'm not going to do that, and I'm going to start a new video and actually work out this problem from start to finish using the isolation technique. And I'll do that in a separate video. But this is how we set up all the pluses and minuses and all the opportunities for us to get started with fractional and whole number values to test in synthetic division.